Welcome back to the best channel in YouTube, Geometry with Mr. Jimenez. So here today we're going to talk about two different definitions. First, we're going to look at the definition of symmetries, which some of us might be familiar with. And then we're going to look at definitions of regular polygons. So a symmetry is a transformation that maps a figure onto itself. It is known as a symmetry of the figure. Okay, so regular polygons. A regular polygon is a polygon whose sides have all equal lengths and whose angles have all equal measures. Okay, so an example of a regular polygon would be this here. Okay, so it's because a polygon is just any two-dimensional shape with straight sides. So a regular polygon would be a two-dimensional shape that all of their sides and angles are equal. For example, this shape here is a polygon, but it's not a regular polygon because the sides are not the same. It's called irregular. We also have this case here, a triangle, which you can say a regular triangle is an equilateral triangle, right? If all the sides are the same and all the angles are the same. Now note that a circle is not a polygon because it has curved sides. And in order to meet the definition of a regular polygon or just a polygon in general, you need to have straight sides. Got that? Okay, so looking at this, symmetries, it's going to be a transformation that maps a figure onto itself. So this has to be a rigid motion, okay? It has to be a rigid motion. And if we have a rigid motion, you know that the two shapes are going to be congruent. Let's look at an example. Here we have a rectangle. We're given diagonal AC and diagonal BD, okay? And what is the minimum angle you could rotate ABCD about M, okay, to have it map onto itself? So we want to rotate this rectangle so that it could map right on top of itself. It could land right on top of itself. So note that a rectangle is full of 90-degree angles, right? And so if I take this and I rotate it 90 degrees, let's see what happens here. 90 degrees. There, it lands right there. It's not yet right on top of itself. So one more 90-degree rotation lands right on top of itself, okay? So note that you could rotate this triangle 180 degrees. And note that that is the minimum angle that you could rotate. Because I could rotate another 180 degrees, and that would be a full 360 degrees in order to map back onto itself. Now let's read question B. Are there any lines of symmetry? Okay, so a line of symmetry, you've seen this before, is just a line that you could reflect over and end up with the same exact image. So this is a very symmetrical shape, and we can see here that I have one line of symmetry and I have another line of symmetry, okay? If I reflect over that line, I'm gonna get exactly the same shape. Now here's another line of symmetry, okay? That horizontal line, and it's going through where? How would I describe those two lines of symmetry? Right? So, of course, there are two lines that pass through the midpoints of its sides. Notice that this here is a midpoint. We have a midpoint here, we have a midpoint here, and we have a midpoint here. So these lines actually cut through the midpoint, okay? Let's see another example. Okay, so here we have an equilateral triangle. In this case, we will call this a regular triangle because it has all sides the same and all angles are also the same. So how many lines of symmetry do you suppose this triangle has? Well, let's see. I see. Remember, it's lines that you could reflect over and get the same exact image. So here is one line. I can see another one here. And yet one more line. So we have 3 lines of symmetry, and they pass through the vertex, right? The vertex, these are the vertices of the triangle, 3 of them. They pass through the vertices and the midpoints of the triangle. And here is the midpoint there, the midpoint here, and the midpoint there, okay? So if I reflect through any of these lines, I will get the exact same triangle. Now let's look at rotational symmetry, right? Because we are familiar with lines of symmetry, but we also have rotational symmetry. And does this triangle have it? Does this triangle have any rotational symmetry? Okay, so I want to rotate B. I want to rotate B so that it goes to point A. And similarly, I want to rotate A so that it maps onto C. That's how this rotational symmetry is going to work. So let's see how we accomplish that. So here is one time, and there it is. We have accomplished our rotation. Okay, now we've done it. We've done it. And how many degrees did it take for us to do that? Well, we rotated by this angle right here. We rotated by this angle. Okay? Notice that because this is a regular polygon, this angle is going to be the same as this angle, and it's going to be the same as this angle. And notice that all 3 of those angles add up to 360 degrees. So in order to figure out how much one of these angles is, I'm just going to divide by 3. So 360 divided by 3 equals 120 degrees. So remember that for rotation, we need to have a center of rotation, and that's going to be where all 3 of our lines of symmetries meet. Okay? And the angle of rotation is going to be 120 degrees. But note that this is the minimum angle that we could rotate by, right? I could also rotate another 120 degrees and still be, right? I could rotate 120 degrees and still have the triangle map onto itself. So how many degrees would be if I rotated twice? That's right, that would be 240 degrees. So let's note here that this angle is the minimum angle. Okay? Now here is your check for understanding. Here is a regular pentagon, right? So what does the word regular mean again? Okay, so here is your check for understanding. Notice it says here that would not carry the figure onto itself. So you're looking for a rotation that would not map this regular pentagon onto itself. See you tomorrow in class.